We develop visualization tools for snow avalanche forecasters. Avalanche forecasting is a complex risk prediction and assessment domain that we found faces challenges of ambiguity and sense making that required targeted visual analytics solutions. Snow avalanches are complex natural disaster phenomena, and they endanger human life and infrastructures that exposed to mountainous and avalanche prone terrain. Avalanche forecasters, like those we partnered with at the forecasting organization Avalanche Canada, are responsible for monitoring and assessing avalanche conditions and issuing daily public bulletins for large regions. These bulletins communicate relevant information about avalanche hazards, like danger ratings and characteristics of potential avalanches. And forecasters rely on a variety of information sources, but one of the most important are human-generated field reports, for instance, those describing observed avalanche occurrences. Field reports are gathered from professional avalanche safety organizations like ski resorts, heli-skiing operations, or those overseeing transportation corridors, and are shared on a web platform called the Industry Information Exchange, the InfoX. Field reports are also crowdsourced from the public. Recreationists share reports on Avalanche Canada's Mountain Information Network, also called the MIN. While visualizations are available in these systems, reports are generally viewed in text data tables. When we engaged with Avalanche Canada to develop more integrated and improved visualization tools for forecasters, we discovered distinct challenges that forecasters face when making sense of these data. First, reports are sourced at point locations that have to be extrapolated across space and time. Also, because reports are generated by humans in a variety of organizations with distinct goals, constraints, and practices, the way that data are gathered and reported varies. These data are inherently incomplete, and this makes analysis difficult. It requires deep sense-making. Forecasters have to rely on their expert knowledge, judgment, and ability to understand the broader context in which these data were generated in order to interpret them. And this is really important given the risk-based context where missing potentially important information could be consequential. Sense-making is more than just retroactive analysis of data according to well-defined questions, and it goes beyond simply seeking more information. It is reasoning that humans engage in when faced with complexity. When the available information is inherently incomplete, sense-making involves coming up with a coherent explanation to reconcile what is observed, to fill in the blanks and make connections. Often, this leads to multiple plausible explanations, ambiguity. We found that ambiguity is a pervasive aspect of avalanche forecasting work. Because avalanches are complex, the data that's available is incomplete and sparse, and is usually generated by humans using free-form text and shorthand, and these data are not tidy. And so forecasters have to rely on their expert knowledge and judgment to make sense of these data. When we started collaborations with the forecasters, we began to explore some initial visualization designs. We started out taking what might be considered a conventional visualization design approach, where we made use of numerical aggregations and summary overviews, using strong visual hierarchies where important information is mapped to the most salient visual feature, and making use of interaction facets to support navigation. But it turned out that forecasters found these visualizations to be confusing and an impediment to their work. They felt that they couldn't trust them. They were concerned that visualizations conveyed a false sense of precision about patterns in the data. And they were concerned that numerical aggregates would hide important distinguishing details about individual reports that might have bearing on what the broader patterns in the data are and how they can be interpreted. To address these concerns, we took a design strategy of desirable difficulty that was first introduced to visualization by Jessica Holman. The premise of desirable difficulty is that by increasing the difficulty or effortfulness involved in a task, one can inspire scrutiny and more careful consideration of data. In our case, instead of relying on a strong visual hierarchy to direct attention through perceptually efficient cues, we chose to create a more nuanced visual hierarchy to give the viewer more attentional control and to require more effort in decoding a visualization. We used packed circle glyphs, where each circle represents a report and encodes various report attributes like avalanche size and avalanche type. And these glyphs, rather than relying on numerical aggregation, support visual aggregation across multiple potential patterns in the data that the viewer can point attention to as they see fit during the analysis. Also, reports are shown individually and provide access to detailed information and tooltips that can be used to contextualize and better understand broader patterns in the data. These glyphs were embedded in a variety of visualization contexts like a map, a timeline, and a matrix showing more abstract categorical attributes of these data. A heat map and an additional freeform text data viewer were also added as part of our collaborations with the forecasters. The forecasters told us that they felt this design worked and it was well suited to what they do, but we didn't really know why it was effective, and this motivated us to conduct a more in-depth study to investigate the sense-making affordances. We wanted to understand how both our designs and the forecasters' existing tools came to support the sense-making involved in their work. The existing toolset included the professional InfoX system and the recreational MIN system, as well as our own ABOBS prototype that we developed. We conducted a study simulating real-world avalanche hazard assessments with 10 forecasters, where we developed 2 scenarios, one that would be presented using each toolset, and we created these scenarios using historical data and materials that forecasters usually would have available to ensure that the simulation was realistic. For each of the scenarios, forecasters completed hazard assessments that include all of the formal measures that would normally be found in a public forecast bulletin. And we split the forecasters into 2 groups, where scenarios were presented in different orders to ensure that any differences were because of the tools and not because of the scenario. InfoX was always presented first in case that AVOBs inspired any unconventional uses of their existing tools. During the task, we conducted a think aloud and used these recordings in a video analysis to code for sense-making processes and uses of either tool. Since we were interested in sense-making processes and most sense-making evaluation approaches and visualization focus on counting insights, we had to adapt a different approach. We took the data frame theory of sense-making from complex cognitive systems and used it as a coding scheme. Here, frames are explanations that set expectations for what counts as data and where to look for it. And we simplified the processes from the original model to differentiate processes that are related to ambiguity, like comparing frames, questioning frames, or reframing, from other sense-making processes, like mapping data to a frame or augmenting an existing frame. We also coded for the context in which sense-making was applied. This included when forecasters were analyzing data using either analytic toolsets or when they were finalizing their judgments and inputting them along the formal hazard measures. And while we found that these two are really closely interleaved, the main focus was on hazard analysis, how tools were used to support sense-making. In addition, we captured analytic actions, which are domain and tool-agnostic analytic tasks that forecasters use in their work. These included drilling down on subsets of data that are of interest, reading data and reports serially in the order that they're presented in, investigating high-level patterns like trends, distributions, or proportions, or focusing on individual reports of interest and closely reading them. And finally, we identified an analytic action that is inspired by information processing theory called gisting. Gisting describes a set of processes for rapidly recognizing and assimilating essential meaning from complex visual information. It's about capturing the essence and pruning away the irrelevant information. It's not just about collecting facts. It can describe how information is processed from a variety of sources like complex visual scenes, when reading and comprehending a body of text, or scanning through data tables. To identify these analytic actions, we used a combination of what forecasters were saying and what they were visibly doing. For instance, we coded for mechanical interactions like cursor movements, selections, zooming, and filtering, the specific view or tool being used, and the patterns that were being investigated. We assessed results using several outcomes and measures. We looked at hazard assessments that forecasters produced, and we also used relative measures of effort devoted to activities like sense-making analytic actions and tool uses. Specifically, we looked at the number of forecasters that ever engaged in an activity, how often they engaged in that activity, and how long they spent doing it. We didn't find any meaningful differences in hazard assessments that forecasters produced, meaning they were still able to do their work with either toolset, but we did find some differences in sense making. First, it's important to note that ambiguous sense making made up a large proportion of sense making, highlighting its importance in this work. And when looking at ambiguous sense making processes like speculating about alternative explanations for data, mentally adjusting data values, weighing the strength and relevance of evidence, or triangulating or comparing different perspectives of the same phenomenon, InfoX seem to have a higher propensity to elicit these behaviors. And while the data produced in this study are messy and incomplete, and this was not meant to be a summative comparative study, there are some clues that might explain this difference. Part of the reason for this may be because of how the information of interest to the forecasters is displayed and accessed in either tool. Forecasters spent a disproportionate amount of effort trying to access report details. When looking at InfoX, instead of using chart views, they chose to read the table view. And in AVOBs, when using the map, matrix, or timeline views, we see that forecasters were spending more time using tooltip interactions rather than looking at high-level patterns. And also, most of the analytic actions we have identified deal with ways of navigating to further details. Only one deals with high-level patterns. Critically, we only observe gisting in the InfoX condition. Perhaps this is because InfoX shows the information of interest, the details, at a glance, where AVOBs introduces additional overhead through tooltips. These findings suggest that in applications involving ambiguous sense-making, where it's not always possible to predict everything that's going to be relevant, relying on summaries alone can be problematic. Emphasizing only certain aspects of the data through overviews and strong and visual and interaction hierarchies that optimize for speed and precision might not actually be optimal. Instead, we recommend that designs encourage scrutiny and reflection and provide fluid access to raw details to ensure that important and relevant information isn't missed. In short, we argue to design for ambiguity rather than to try and design it away. And we draw some broad design implications from this research. Specifically, we find it's important to not unilaterally try and remove cognitive difficulties, as it's an important part of the process. This might involve trying to relax visual and interaction hierarchies to not overly emphasize certain aspects of the data and allow the viewer more agency in where they want to direct attention. Also, providing access to base details across multiple levels of data granularity can ensure that the viewer can refine their understanding of broader patterns in the data. And lastly, both the distinct tasks of sequentially reading and constructing a narrative and gisting or scanning for details are currently not well supported in visual analytics systems. Given how important they are in complex sense making, we argue that they need to be better understood and better integrated. Our study has some limitations, namely that it's an exploratory, informative ethnographic research study that has issues of reliability and validity. And we note that evaluating complex reasoning during analysis, especially with experts, is problematic. A lot of what forecasters do is tacit, and it might not be verbalized, and the account that we captured is therefore inherently incomplete. The AVOBs prototype, along with other visualization tools that were developed as part of this research, are currently seeing active operational use by a variety of avalanche forecasting organizations. In the future work, we aim to study these tools in the field. In addition, future work may also focus on more rigorously studying and understanding gisting as an analytic action.